denote that as CT, the ciphertext transmitted, and user B will receive that message. Now, for some later cases, I'll write this to receive the CR. A little bit strange, but in this case, CT and CR are identical, they're the same. I transmit the ciphertext, it goes across the network, something's received by B. What is received by B? The transmitted ciphertext, except I've given it a different name. I'm going to say what's received is CR. In the normal case, they are identical. So the ciphertext is transmitted and received, but later when we see some other attacks, they make it different. So I give them different names of what's sent and what's received. What B does when they receive a message, for confidentiality, they want to see the message, so they decrypt. And we'll write that we obtain PR by decrypting. What's the key we use to decrypt? KAB is a shared secret key. B receives a message from A, therefore we'll use KAB to decrypt. And they decrypt what they receive, and they get some value PR, the plaintext received. In this case, we'll assume that there's no attacker in the middle at this stage. So CT and CR are the same. That is CT equal to CR? Yes, in this case. Later we'll see no. Just for this initial case, they're the same. So we could have written this equation instead of CR and PR, CT. Does PR equals PT? Does PR, the plaintext received, equal the plaintext transmitted? Yes. Why? Let's look at our assumptions. Yes, I think it's obvious, but let's make sure that our assumptions capture that. Decrypting a ciphertext with, so assumption A6 on this list, the right one, decrypting a ciphertext with the correct key, the same key that was used for encryption, will produce the original plaintext. So that's the assumption that tells us that yes, the plaintext received will be the same as the plaintext transmitted. Our assumption, if we use the correct key, and we can see KAB was used to encrypt, KAB, the same key is used to decrypt. If we decrypt CR, which is actually the same as CT, we will get PR being the same as PT. We assume that's the case. That's the obvious case. We get the same plaintext back. So B gets the plaintext. What if, and I will see that in a moment, let's see an attack. From confidentiality perspective, we now have a malicious user, and the malicious user in the middle. Instead of C calling him C, we're calling the malicious user. Okay. Now, the malicious user, what do they know in this case? The attacker, all the things that they know. Let's have a look at the assumptions. If you scroll down the assumptions, we saw what the attacker knows. It's on the sides as well. We assume that the attacker knows all the algorithms used, so they know what was used for encrypting and decrypting, whether it was DES, AES, or something else. We assume that the attacker can intercept any message. A message was sent across the network. The attacker can get a copy of that message. They know C, CT, or CR. They're the same in this case. The attacker does not know the secret values. In our case, they do not know KAB. We'll assume they do not. Alright, the last assumption is about brute force attacks. They can't do brute force attacks unless the length of the key is less than, I put a number here, less than about 80 bits. Now that's not precise, but assuming the key is long enough, they will not be able to do a brute force attack and discover the key. So the attacker knows the algorithms, they know the ciphertext, but they don't know the key. The malicious user in this case, they have, let's say CT, what was transmitted, it's also the same as CR. They know the encryption algorithm, They want to find the plaintext or the key. They can't guess the key because it's the length such that they can't do a brute force attack on. So what do they try to do? To get the plaintext, what the attacker can try to do is decrypt using some key, CR. What key can they use to decrypt CR? Any key they like, except one. We'll assume that they cannot use KAB because they don't know KAB. I'm going to say any key, well they can use a key, but we'll assume that they're not lucky and they can guess KAB because it's so long that there's the chance of guessing it is so small. So we'll assume whatever the key they try here, it is not KAB. Doesn't matter what we denote, K malicious, whatever key they choose, where the key they use is not equal to the KAB. That is, they don't know KAB. So if we decrypt the ciphertext using some key other than KAB, we get some plaintext. The plaintext that we use. Using the key that they chose. The key that they chose is not the same as KAB. They get some plaintext as output. They apply the function, they get output. Some plaintext, I denote as the plaintext the malicious user gets. Is that value the same as what A started with? No, it's not. And that's one of our assumptions.
Yeah.
A7, decrypting ciphertext using the incorrect key will not produce the original plaintext. Okay, so we've used a different key, therefore we assume we will never get the same plaintext. And in fact, the malicious user will be able to recognize that this is wrong. They will know that it's not the right plaintext, but that's of no use to them. They want to get the correct one. No, it is not. Okay. This is just showing that we've achieved confidentiality. We've sent a message from A to B. B decrypted and got the original plaintext because they had the key. observe past communications and have seen past pairs of past ciphertext messages, different ones, and somehow have managed to learn the corresponding plaintext values. And that's a common assumption in practical attacks, that the attacker, so this is a slight extension, the malicious user also knows pairs. Like, they know that in the past there was some ciphertext, some old ciphertext that was sent from A to B. They know it was encrypted with the same key, and they also somehow discovered the corresponding plaintext. This is what we say is a known plaintext ciphertext pair. It's easy to get the old ciphertext values, just intercept many packets, many messages. And after they get the old plaintext message, and they don't know the key, maybe the message was released through some other means. Maybe the message was forwarded to the enemy key secret. So therefore, the attacker knows about that. Therefore, the attacker now knows an old ciphertext value, an old corresponding plaintext value. They don't know the key to get from one to the other, but they know the pair. They could try to use that to help them find the key so that they can decrypt the new ciphertext value they've intercepted. So practical attacks may use past values to try and help. The secure algorithms, it still doesn't make it easy to find the key or decrypt the ciphertext. So from AES, for example, there are no known attacks. Even if you have ciphertext system that help you to get the key. So no, that doesn't help. I'll assume it does not help. Even if you know many of these, it doesn't help. So, confidentiality service. Well, there's nothing they can do under the assumptions that we're working on. Assuming they can't find the key, and we assume that, because it's long enough, like sure as a key KAB, which was long and random. So the only way the attacker find it is to guess it, and we know it's going to take too long to try and guess that. So they can't find the key. Assuming the algorithm, the encrypted decrypted algorithms are strong, there are no flaws in them, AES is considered that, then there's no way for the attacker to find the plaintext distance, and that gives us our confidentiality. That's why we concept security. Confidentiality is easy to provide compared to some other services. Use a strong encryption algorithm and use a large key. Right, but there are some practical problems of ensuring that the key is kept secret. If the attacker does find the key, we have a problem. We'll assume they cannot. Another service that we like to provide, or two others which are related to similar techniques, are authentication and integrity. Integrity is about if we send a message from A to B and someone in the middle changes it along the way, can the receiver detect that that change was made? If they can detect the change was made, then we can maintain integrity. If a change can be made without the receiver knowing a change was made, then that's a compromise of the integrity of the data. So authentication is about if someone sends us a message pretending to be A, but they're actually the malicious user, and we think it's from A, then that defeats the authentication service. We want to be able to be sure that the message came from A, not someone pretending to be A. So we look at how encryption provides those services as well. So we'll look at some variations on this where the malicious user doesn't just intercept the message, but they may intercept and modify the message. And we'll try to see if the malicious user can modify the message without the detecting that it was modified. If they can, then that attack is successful. Let's go through some scenarios. Draw this again. Same scenario, user A, user B. We start with a transmitted plaintext and a corresponding transmitted ciphertext, which is obtained by encrypting with KAB. We're sending from A to B still, the plaintext, and we transmit that. We transmit CT. Now, let's have the malicious user intercept this message before it gets to B, not just let it go through, but intercept it and try to make a change to that message, with the hope of sending a message onto B, and B thinks it's the original message from A, but it's in fact a modified message. Let's see if that's possible. So what happens now is the malicious user gets a copy. What can they do when they receive CT? Can they read the plaintext? Can the malicious user read the plaintext when they get the ciphertext? No, we just saw in the previous case they cannot. It's encrypted, they cannot read the plaintext. But they could try to make up some different plaintext and encrypt that and forward it on to B with the hope that B thinks that was the message from A. Let's try that and see what attack may be possible. Let's say that the malicious user gets this ciphertext and modifies it first. And send the modified version onto the user B. That is, the modified one I'll denote as CT prime. And mark up the top prime, just to say that they've changed the ciphertext. Maybe the ciphertext was a million bits, they changed some of those bits to try to perform an attack. Let's see what happens. Where CT prime is different from CT. Different values. We send it on to B. B receives some ciphertext. I'll denote that as CR. From B's perspective, it's received some bits, some ciphertext. What does B do next? Decrypt. Right, you receive ciphertext, you decrypt. You decrypt what you receive. Decrypt using a key, CR, and we'll get some value. I'll denote as PR. What key do I use to decrypt? KAB. I received a message from A. I think it's from A. The from message, the from field in the message says A. I am B, so I use key KAB. what happens at B now? It gets the wrong plaintext, or it gets recognisably wrong plaintext. That assumption is which number? It's maybe not captured here directly, but it's based upon A7. If we use the wrong key, we'll get the variation of A7 here is if we're using a different key, or in fact it was a different ciphertext, in fact, we'll get the wrong, recognisably wrong plaintext, because CR is the same as CT prime. CT prime is different from CT. Okay, we're trying to decrypt the wrong ciphertext here. So we're going to get some plaintext that is different from PT and recognisably wrong. So what will happen? B recognises that the plaintext that they give from the decryption is wrong. It's just random characters. They expect some English message or some structured message. They decrypted using a key, some ciphertext, which was not obtained from an original structured plaintext. It was a different one. So B recognises that PR is wrong. So I think the assumptions we've got, we really should have another one that is variation of A7, is that it's slightly different. Here we say decrypting with the wrong key, but in the same way, if you decrypt different ciphertext, the wrong ciphertext, you will not get you'll get a different plaintext. Decrypting two different ciphertexts will give two different plaintexts if you use the same key. Because CR is different from CT. B recognises the plaintext is wrong. It looks like random characters, it's not a structured message, and therefore has detected something's gone wrong. They don't trust the plaintext and discard it. So that's a case where the attack, the malicious user trying to modify something, is detected. We don't know how they modified it, but we know something went wrong, so we discard what we received. We don't trust it. We'll try some variations. What could the malicious user try to do such that B doesn't detect that? There are a couple of other choices. What could you try? Today's a chance to put on your malicious hat, your black hat, and try to do some bad things. What could you try to do as a malicious user so that B doesn't detect a change? Try to change the plaintext. That's effectively what we did there. If we modify something here, let's say we choose a new plaintext, encrypt that with a key, the key of the malicious user, and send ciphertext on to B. Similar issue as before. If we have a new plaintext by the malicious user, then the key that was used to encrypt cannot be KAB. Let's try that one. So the application of these assumptions is to apply them or to use the logic to see how they can be used to provide the services. Malicious user. They choose some new plaintext. PT prime. Different plaintext. They want to say this plaintext was decrease the malicious user's salary by 10,000 baht. They change it to increase. So they just try to have a new plaintext and try to fool B into getting that. They choose a new plaintext and they encrypt that new plaintext with a key. And get a new ciphertext. What key do they use? Or maybe the difference. What key do they not use? They cannot use KAB. They use some other key. You'll notice the key of the malicious user, but it's not KAB because they don't know that. They get some ciphertext. And because it's a different key, we'll assume that the ciphertexts are not the same. CT is not the same as CT prime. We send that on. And you send CT prime. User B receives that. They receive CR, which is in fact the same as CT prime. They receive that and try to encrypt. The key we use to decrypt the user B, KAB, we'll still take it from A. We decrypt CR, it's the same as CT prime. We provide that as decrypting with KAB. CT provides a different ciphertext. CT prime was obtained by encrypting plaintext with K of the malicious user. Here we try to decrypt with the incorrect key. Encrypted using K of the malicious user. We try to decrypt with a different key. Our assumption A7 says if you try to decrypt with an incorrect key, you will get the right plaintext and the plaintext. Again, B gives plaintext. Here, I'll take the R as well. Attack detected. So the use of encryption not just provides confidentiality, but also provides protection against replication attacks. This is the attacker trying to modify the data, and it provides the data integrity service. Data integrity is that if something modified, in the previous case was the ciphertext is effectively the same, but then use a new ciphertext. B detects that because we're using a different key to decrypt. Is there anything else a malicious user could try to do without knowing KAB? I think if you try to consider all the scenarios, you will not because B will always detect. They need KAB. If they want to modify something, they could choose a new plaintext. If they did have KAB, then they could fool B into getting the message, but they don't have KAB, so therefore they cannot be receiving that online message. So this is providing data integrity. The next one we'll do is providing authentication. That is, let's try to do a masquerade attack. The malicious user will pretend to be A. We've got user B. Start again. User B. There is no user A here. We'll start with just a malicious user. What they do is they send a message to user B. They choose their own plaintext message. Let's just call it P. They encrypt that with a key and give some ciphertext and send the ciphertext to user B. But they say that this message is from A. What key do they use? Let's make some more space. What key are they going to use to encrypt? The malicious user is going to use KAB. They don't know KAB. User A knows, so we don't use A here, we're a different user. User A knows KAB, user B knows KAB, but the malicious user does not. But they want to pretend to be A. So they have a message, they want to pretend to be A, they encrypt it with a key. But again, they cannot encrypt with KAB. There must be some other key. If they did have KAB, they could perform an attack. They encrypt with something. Send the ciphertext to B, and as before, B does all encryption steps. Decrypt using which key? If we sync the messages from A, decrypt with KAB. The ciphertext. Say we get some plaintext P prime. Is P prime equal to P? Malicious user chose a plaintext, encrypted it using K of the malicious user, obtained a ciphertext, sends the ciphertext to B, pretending to be A. A therefore decrypts with KAB, different key. If we decrypt the ciphertext with the wrong key, we get the wrong plaintext, different plaintext. Therefore P prime is and are they the same? No. And the assumption decrypting ciphertext using the incorrect key will not produce the original plaintext. They understand. And the decrypt will be able to recognize that this plaintext is wrong. The plaintext will be unrecognizable output. So P, we say is wrong. Attack is detected. B detects it once received as wrong and decides that it doesn't trust it. So this is a masquerade attack. Malicious user is masquerading as A, pretending to be A, send a message to B, B detects it, and therefore the authentication service is provided. B can authenticate that this message is not from A, they can confirm. So we could use such a technique, so when you send me emails, I can confirm who's the original sender, or if it's someone pretending to be someone else, if we use this form of encryption. There are maybe small variations that we could try. I think if you work through them, you'll see that there's no way that malicious user without knowing KAB could do something and have B fooled into thinking it was from A, and that's what we need for integrity or authentication. You need to look at these problems logically. Now, you don't need to understand how the algorithms work, but you need to follow the logic and apply those assumptions to see why we provide these services. Any questions? Okay, in the back. Yeah? The first attack, the malicious user changed the ciphertext. The ciphertext was intercepted. Let's say the ciphertext was a 1 megabyte file. The plaintext was a 1 megabyte file. It was encrypted and produces a 1 megabyte of ciphertext. When you intercept it, it looks like 1 megabyte of random bits. A good encryption algorithm will take the plaintext and produce random output. So the attacker sees 1 megabyte of random bits. They don't know what it means. They can't get the plaintext, but they can modify it to change some of the bits. So you can modify the ciphertext. Okay, with the first one, I don't have it here. We can modify the ciphertext, but the point was that B detected it was modified. So the modification attack, and the same with the masquerade attack, easy to do, easy to try from the attacker's perspective. Hard to stop them from trying. They can try, but it's possible for B to detect that they did it. The detection, there's access security mechanism. Since we detect that they modified it, then we know don't trust this message. So we can modify anything. You send a message to someone, I intercept before it gets to them, I can change it, but the receiver will detect that I've changed it, and therefore not trust that message, and that forms a security service. Any other questions before we look at some other techniques? Still on authentication. Trying to stay with us through this lecture because these are the key principles, and I see some tired faces. But these are the key building blocks of what we use many of the other IT mechanisms, IT security mechanisms. Let's return to the slides briefly. And we will not say too much about the things that we've missed. So some topics in this cryptographic slides we'll skip over. We've talked about attacks, brute force attacks. We've talked about the speeds yesterday. The assumptions about what the attacker knows we've covered. We said the ciphers operate on small blocks, 64 bits, 128 bits. They encrypt a block at a time. The ways to take a large file, split it into blocks, encrypt the blocks, and combine them back together to get the final encrypted file, there are different methods. They're called modes of operation. We will not cover them, but if you use some of the software in some assignments, you may need to be aware or at least know that there are different modes of operation. And the list of common ones you'll see are listed here. ECB, CBC, CFB, OFB, CTR, and there are others, are ways to deal with a large file and how to break it into blocks and encrypt the blocks and join them back together. There are different approaches for doing that, which we're not looking into in this course. There are also stream ciphers. Block ciphers usually encrypt 64 bits or 128 bits at a time. Stream ciphers usually encrypt a byte or even a bit at a time. They use different algorithms. But we will not look at them either today. Let's keep moving. RC4 is a popular stream cipher used in Wi-Fi but has flaws in it. So we're good. And using encryption to provide confidentiality, make sure no one can see a message. And we've just seen some cases of using encryption to provide authentication and data integrity. That is, no one can modify our message without being detected, or no one can send us a fake message without being detected. There are other ways to provide authentication, not just with symmetric encryption. There are different ways for providing authentication. So just to recap, when the receiver receives a message, they would like to verify that the contents of the message haven't been modified along the way. So make sure nothing's been changed, and that the source of the message is where they claim to be. No one's performing a masquerade attack, so we can authenticate the source, or the general aims. There are different ways to do that. We saw some cases using symmetric key encryption to do this, provide this authentication service, but there are other approaches that use message authentication codes, MACs, use hash functions and symmetric key encryption, and public key encryption. And we're just going to look at one more of them, which is using the last one, public key encryption. And it leads us to an important concept called digital signatures. So we're not going to look at message authentication codes. They're available. We will need to look at hash functions to understand digital signatures for just the basic concepts. But so what we'll do for the rest, how long we've got left, not long, we'll introduce the basic concepts of them and public key encryption. I think we'll go direct to public key encryption, and that will be enough for today. So let's jump through to public key encryption. Symmetric key encryption, encrypt with a shared secret key like KAB, decrypt with the same key. Right, that was symmetric key encryption. The keys are the same on both sides. The other approach, what's the opposite of symmetric key encryption? What's the opposite of symmetry? Asymmetry. Asymmetric encryption, encrypt with one key, decrypt with a different key. So they're different on both sides. And the other name for asymmetric key encryption is public key encryption. Right, so it has different names, and we'll see why shortly. Symmetric key encryption was used from maybe 2,000 years ago up until maybe the 1950s and 1960s, and still used today. But in the 1970s, maybe, around that time, people discovered a new approach, or designed a new approach called asymmetric key encryption or public key encryption. And different people had a large influence on that. Diffie and Hellman. We'll see there's an important algorithm, the Diffie-Hellman key exchange, developed an important public key encryption algorithm, or public key algorithm. And another one by Ravesh, Shamir, and Edelman developed what's called RSA. RSA is a public key encryption algorithm. So these are some important algorithms that we'll see used in practice later in the course. So today, let's just talk about the concept. Symmetric key encryption algorithms use the same key for encryption and decryption. Asymmetric algorithms use one key for encryption and a different, but related key for decryption. In symmetric key encryption, if I ask you to choose a secret key, how would you choose that secret key? Guess first. Let's be a little bit more scientific about it, or a little bit more precise. How do you think you should choose your secret key? Guessing? Alright, I think of a number between 1 and 10. Well, now we need a 128-bit number. So what are you going to do to choose a secret key? Probably you'll use a computer to generate a random number. You'd like a random value so that someone else can't guess it. If you guess it, or if you try to write one down,